They are capturing photons racing through space, measuring their energies, and pinpointing their sources. An army of high-tech instruments, including the Hubble Space Telescope, is peering into ever more distant corners of the universe. They are reeling in enormous volumes of data that scientists use within models to explain how galaxies took shape. How stars live and die. And how the universe set the stage for life. What are we learning about the origins of our world and ourselves in this Age of Hubble? There is a clarity, a brilliance to space that simply doesn't exist on Earth, wrote the astronaut Gus Grissom. Nowhere else can you realize so fully the majesty of our Earth and be so awed at the thought that it's only one of untold thousands of planets. For astronauts and stargazers, the universe beckons us to explore and to wonder. How did it all come about? And how do we fit in? Are there other worlds like our own, rich with life? Today, these questions are being raised anew by bold advances in the science of astronomy. The Hubble Space Telescope was launched in the year 1990 to capture the pristine light of distant space. It led a fleet of space-based telescopes sent up to probe distant galaxies, black holes, stars, planets. The vantage of space allows satellites to capture light that is blocked or distorted by Earth's atmosphere. From long-wave infrared light that passes through dust clouds, revealing hidden structures in star-forming regions or galaxies, to high-energy X-rays from supernova explosions or the environments of black holes. By the time the light of these objects reaches us, it has traveled millions or even billions of years. It carries with it information about how the universe came to be what it is. Sending telescopes into space was part of a larger technological revolution. On mountaintops around the world, scientists began building a new generation of giant telescopes. Among them, the Very Large Telescope Array, or VLT, in Chile. The Keck, Subaru, and Gemini telescopes on the summit of Mauna Kea in Hawaii. These high-tech instruments are equipped with the largest mirrors ever built. They have to be nearly flawless to capture the trickle of photons from distant reaches of the universe. The VLT mirrors, for example, are so smooth that if you blew one up to the size of Paris, its surface would vary by only a millimeter. To the powerful light-gathering abilities of these precision mirrors, scientists added computer programs and sophisticated optics designed to cancel out distortions in starlight caused by turbulence in our atmosphere. The purpose? To gain the clarity of space here on Earth. Scientists have now added a powerful new weapon to their arsenal of discovery. Supercomputer programs that use the laws of physics to simulate important cosmic events. They use these virtual telescopes to literally set the universe in motion. To test theories about how the cosmos evolved on the largest scales, and how objects form and interact. From immense galaxy clusters down to solar systems and planets. Among the most important revelations in this Age of Hubble is a deepening sense of the scales and the forces that define the universe. Based on their view of the night sky, the ancient Greeks saw Earth at the center of creation. The philosopher Aristotle described a series of 55 celestial spheres, with each moving in a way that predicted the positions of planets or stars within them. The stars, he said, are made of a pure substance not found on Earth. Thus, the outer spheres they inhabit are home to the gods. Centuries later, scientists would learn that Earth revolves around the Sun in an assemblage of planets, a solar system. A century ago, they deduced that our Sun is one of billions of other stars moving around a disk-like structure, the galaxy. What lay beyond this island universe? How far did space extend? Working with the new 100-inch telescope on California's Mount Wilson, astronomer Edwin Hubble and an assistant named Milt Humason analyzed the light of blurry patches of sky known as nebulae. They found that these patches were actually galaxies unto themselves, located far beyond our Milky Way. Many of them, in fact, are moving away from us. The farther away they are, the faster they are receding. These findings sparked the rise of a whole new model of the universe. It's much larger than we imagined, filled with countless galaxies and growing larger all the time. Over 6 decades later, scientists launched Hubble's namesake, a telescope in space, to nail down the parameters he helped define. The cosmic expansion rate, as well as a scale for calculating distances. Knowing these two numbers would allow astronomers to establish a timeline for cosmic evolution, going all the way back to the earliest moments of time. The starting point comes to us courtesy of the so-called cosmic microwave background radiation, light emitted not long after the universe was born. Reading this light, the COBE, WMAP, and Planck satellites showed that the universe began with widespread variations in its density. From this blotchy pattern, gravity sculpted the arrangement of galaxies we now see in our telescopes. Our galaxy and its neighbors are tied to a larger grouping, the Virgo cluster, some 50 million light-years away. It's at the center of a supercluster, 10,000 galaxies strong. From this intergalactic hub, filaments of galaxies extend outward in all directions, forming a vast luminous web. How far out does this cosmic web extend? How did it come to be? And how will it evolve in the future? Astronomers sought answers in even more precise measurements of cosmic expansion. Using a combination of Hubble and ground-based telescopes, they looked for a type of sun-like star that had burned itself out, called a white dwarf. If one of these tiny dense remnants happens to orbit another star or another white dwarf, it may begin to draw mass from its companion. At a critical threshold, it begins to undergo a thermonuclear reaction. Scientists at the University of Chicago and Argonne National Lab have been simulating the chain of events that follows. Hot ash begins rising to the surface. As it breaks out, it wraps around the star. A collision on the other side triggers the explosion. These Type 1a supernovae are thought to all explode in the same way, with the same luminosity, wherever they are in space. And because they are so bright, They are ideal for measuring extreme distances. It's like looking at cars with identical headlights approaching on a highway. The dimmer they appear, the farther away they are. But when astronomers began looking at these cosmic beacons, they noticed something unexpected. They combined their brightness with another measure, how far their light had shifted to the red. The larger the shift, the more the universe had expanded since the star had exploded. Some explosions looked dimmer than expected, based on their red shift. That meant their light had traveled an even greater distance to reach us. That led astronomers to conclude that the cosmic expansion rate was slower in the deep past. It must have accelerated for the universe to reach its current size. The force causing space to speed up is still unknown. Scientists refer to it as dark energy, and it may be all around us. Far from being empty, the vacuum of space is filled with energy that constantly wells up in the form of particles of opposite charge, matter and antimatter. According to a theory that has gained wide acceptance, the universe began when this vacuum was somehow tipped into a higher energy state, causing space and time to suddenly inflate. Tiny fluctuations in the primordial energy generated pressure waves or ripples. They gave rise to density variations, which gravity amplified over time into the web-like structure seen in telescopes. Taking cosmic expansion into account, galaxies out at the edge of the visible universe are 46 billion light-years away from us in each direction. There may be much more to it. The fury of cosmic inflation would have caused the universe to go from atomic size to cosmological size within an infinitesimally short time. The universe as a whole would have grown to some 10 billion trillion times the size of the observable universe. Put another way, the new theory says the whole universe is to the observable universe as the observable universe is to an atom. So where does that leave us in the grand scheme of things? Since the discoveries of the solar system and the galaxy, we find ourselves confined to an ever smaller corner of creation. And yet, in this age of Hubble, we have learned just how much we are a product of the universe. And of a great cosmic continuum that reaches back to the beginning of time. In a sense, our own story looms large. It began with the earliest generation of stars and galaxies, at a time when the universe was awash in hydrogen gas. When the first stars formed, they began generating oxygen and carbon in their cores. Some exploded, generating heavier elements like iron or gold or magnesium. While spreading these elements far and wide in the form of dust. This animation depicts a supernova spotted by Chinese astronomers in the year 1054 AD. The star was utterly destroyed, except for a spinning, ultra-dense core the size of a city, a neutron star, and an expanding cloud of gas and dust, still growing at a rate of 1,000 kilometers a second. Astronomers have been poring over the Crab Nebula. What they found is that the filaments of matter that roared out of the blast contain large volumes of dust, an array of mostly carbon or silicate compounds that absorb visible light. These solid particles are crucial for the formation of solar systems. Within the Crab Nebula, there is enough dust to make some 30 to 40,000 Earths. Over time, and after countless stellar explosions, dust has collected in dense pockets throughout our galaxy. But dust grains can be found throughout intergalactic space as well. Some might have come from the earliest supernovas. There is another source as well. Since the 1960s, astronomers have been studying bright beacons of light that shine from the centers of distant galaxies. A quasar's power source, they've found, is a black hole that has grown to millions, even billions of times the mass of our own sun. The thinking is that magnetic fields leap off a disk of matter that's spiraling into the black hole, drawn by its extreme gravity. These fields channel a portion of the inflowing matter out into powerful particle beams. The jet is part of a larger rush of matter away from the black hole. You can see it in a large spiral galaxy called NGC 3783. 30 million light years from Earth. Astronomers use the Very Large Telescope Array in Chile's Atacama Desert to peer into the core of this galaxy, to study the environment of a supermassive black hole. From a disk of matter flowing into the black hole, intense radiation had created a dusty wind that is moving up and away from the black hole. The source of the dust is likely generations of giant stars that lived and died in the galaxy's central region. Black hole winds are now thought to have had a major impact on the universe at large. You can see it in a simulation of early cosmic evolution. From a starting point 12 million years after time zero, this computer simulation shows the evolution of a cosmic patch some 350 million light years across. Not everything is known about what happened, including the nature of a dominant substance known as dark matter. Within the volume of this simulation, tens of thousands of galaxies take shape all along the strands of the cosmic web. Where the filaments intersect, something happens that will affect the character of every galaxy, star, and planet. Gigantic bubbles of hot gas begin to expand outward. They form when matter flows into large central galaxies and gets blasted out by supermassive black holes lurking in their cores. In time, these hot bubbles push out well beyond the central galaxies. This has the effect of limiting the amount of gas that can fall into central regions, allowing smaller galaxies like ours to form on the periphery. The bubbles spread huge volumes of gas and dust created in earlier generations of stars. Galaxies all around the universe bear witness to this dusty legacy. The bright central region of the famous Pinwheel Galaxy is surrounded by dark, dusty lanes. In spiral galaxies, the most common type, hot winds from exploding stars helped push these clouds toward the periphery. as well as above and below their flat disks. You can see evidence of this in our view into the disk of the Milky Way galaxy. Dark dust lanes and ominous clouds dominate our view into the disk, while tendrils of dust reach far above it. Here, above the plane of the galaxy, just 400 light-years from Earth, is a dense, irregular cloud of dust called Lupus 4. Our Sun, our solar system, likely formed in a cloud like this. Lupus 4 may one day give rise to a star cluster like NGC 3590, a region of dust and glowing gas near the plane of the galaxy. These young stars were probably all born at the same time, within the same cloud. The manufacture and spread of dust is an ongoing process in our galaxy. Consider the Carina Nebula, located 7,500 light-years away. It spans some 250 light-years across. At its center is the giant star Eta Carinae, one of the largest and most unstable stars known in our galaxy. It is surrounded by an expanding bipolar cloud of dust and gas, known as the homunculus, or little man in Latin. Astronomers believe it was expelled during what they call the Great Eruption in the years 1838 to 1845. With a mass over 100 times that of our Sun, this star could explode at any time. And yet, in the larger cloud of dust and gas, stars are being born at a fever pitch. Here, a pillar of dust is being eroded by a torrent of ultraviolet light from hot, massive stars nearby. A dense region at the top resists these scouring winds, giving a young star time to incubate. Gas and dust flowing into the star are being blasted out in jets coming from its poles. Of all the constellations, few attract more admirers than Orion. Within it is a stargazer's dream. The Great Orion Nebula, a luminous castle of gas and dust, 1,300 light-years away. It's roughly the size of a full moon on the sky. At its heart is a star cluster called the Trapezium, a brilliant formation first discovered by Galileo. It pumps out a wind of ultraviolet radiation that causes the surrounding region to glow. These large stars emit streams of charged particles that collide with dust clouds, forming a frothy landscape of arcs and bubbles. These winds are also disrupting the growth of hundreds of solar systems in the making. Despite these winds, some solar systems still manage to come to life. Using the Hubble Space Telescope, scientists have been drawing them out of their bright and hazy surroundings. Thousands of solar systems are being born in and around the Orion Nebula, in a rich chemical soup provided by large exploding stars. Amid all the dust, scientists have detected huge volumes of water. Where does it come from? And how does it form? In some cases, water is the byproduct of a star's death. When a medium-sized star like our Sun uses up the hydrogen in its core, it becomes unstable, shedding its outer layers. The Helix Nebula is a star that has puffed out into a colorful ring of glowing gas and dust. A tiny remnant of the original star, called a white dwarf, scours the ring with harsh ultraviolet light that destroys particular compounds, including carbon monoxide. The oxygen that's set free combines with hydrogen in a molecule that forms water. Dying stars are not the only source of water. 750 light-years from Earth, a protostar called L1448mm is shooting matter out in high-speed jets containing oxygen and hydrogen. When these molecules reach a cooler environment, they form water at a rate 100 million times the flow of the Amazon River. Water then becomes part of the dynamic of a solar system's birth. Scientists have sought to better understand the formation of planets by simulating it in a supercomputer. Gravity causes a central region to collapse and dust and gas to flow in. It forms a disk that swirls around the newborn star. Along the way, water acts like a glue, allowing dust grains to form larger bodies, from rocks to comets, asteroids, and finally planets. Up on the high deserts of Chile, Astronomers have been using the Atacama Large Millimeter Submillimeter Telescope Array to peer into the turbulent environments of newly born stars. One of them, 450 light-years away, is known as HL Tauri. The star is no more than 1,000,000 years old, but there are signs that planet formation is already underway. Its hot core is cocooned in a cloud of gas and dust, the solar nebula. As matter flowed into the star, it has settled into a protoplanetary disk. This disk has a series of telltale grooves where the gravity of planets has begun to sweep up the dust. Dust within the solar nebula carries all the material needed to build a planet like ours, including organic compounds. So, how did Earth get its water? The answer may begin with our star. As the sun vents heat from nuclear burning in its core, it generates a steady wind of protons that reach to the edges of the solar system. This wind encounters dust particles that are wafting through the solar system, attracted by the gravity of planets. Some 40,000 tons of dust and rocks rain down onto the Earth each year. Leftovers from the birth of the solar system 4 to 5 billion years ago. Interplanetary dust has long been known to carry organic or carbon compounds able to survive the journey through Earth's atmosphere. Scientists recently found something else on the dust particles themselves. Hydrogen ions, or protons, from the solar wind strike these particles. When these protons interact with oxygen in silicate mineral grains, they form H2O molecules, which then cling to the particles. This process was documented in lunar dust grains picked up by Apollo astronauts. It may be the source of water ice that is collected in the bottom of some lunar craters and is strewn about lunar landscapes. In addition to watery dust raining down onto the Earth, this may explain how comets and asteroids were able to generate stores of water and to bring them down to Earth. Given that water is created and spread so readily, it's not surprising that it pervades our own solar system. At its edges, Pluto and its moon Charon are lined with a thick layer of frozen methane and water ice. The blue planets Neptune and Uranus get their color from the methane clouds that make up their frigid atmospheres. Within, Charged particles circulate in a sea of liquid water, producing electrical currents and magnetic fields. Within the folds of Saturn's rings are countless particles of ice. Hovering just above them is the moon Enceladus, with an icy surface that makes it one of the brightest objects in the entire solar system. The Cassini spacecraft detected jets of water ice shooting out of its south pole. Scientists believe they are coming from an interior ocean, launched by the squeezing action of Saturn's gravity. The largest planet, Jupiter, harbors its own storehouse of water. The storms that drift along its surface are the result of water vapor rising and falling like thunderstorms. Beyond Jupiter's roiling atmosphere lies a water world, Jupiter's second moon, Europa. Its bright, smooth surface is crisscrossed by channels and grooves carved out by shifts in an ocean of liquid water or slushy ice that lies below. The faint emissions of water jets, illustrated here, were recently picked up by the Hubble Space Telescope. Then there's Earth, a water planet. Vast interconnected bodies of water, the oceans, cover 71% of its surface. And now, scientists have detected whole oceans hidden in rocks deep inside the planet. The story of dust and water is central to our understanding of how life can arise. These two components can be found throughout the galaxy. But does life inevitably follow? For now, Earth remains our only data point among the thousands, even billions of habitable worlds that may be out there. The Age of Hubble has brought a new appreciation of how we emerged in a universe that is immense beyond imagining. We have only begun to discern its limits. New data supports theories of how the universe began in a furious expansion. Because science is fundamentally concerned with events that repeat in nature, some inflationary theories place our universe in an even broader cosmic landscape. The idea is that universes, like frothy bubbles, extend out into the voids of infinity. The Age of Hubble has brought incredible advances in our understanding of the universe. It is surely only the beginning of a long quest to know how it all fits together, where we came from, and what the stars may tell us of our place in the spread of time and space. For astronauts and other stargazers, there is both a sense of wonder and connection as we lock our gaze on the heavens, searching for the secrets of creation emblazoned on the night sky.